Hi, good morning, everybody. I think everybody should be connecting just now. So I will take a few seconds for the introduction so that if anybody is having any connection issue, they have time to connect. And actually on our side, we have some technical trouble, but it should be all right for all of you. So welcome to that webinar. We are really happy to welcome you. We will be talking today about yield improvement for microprocessing. And there will be a presentation from John Lopez, myself, Gwen Pallier, Jérôme Patas, and Girolamo Mintundi. And if you want, there is a chat on the right, on the bottom right. You can ask questions. If you have any technical questions for connection or anything, it will be there. Or if you have questions about the presentation, you can add them there as well. At the end of the full presentation, we will be answering all of your questions. So I leave the floor to John for his presentation.
Okay, thank you, Gwen, for the nice introduction. And ladies and gentlemen, welcome to my talk. So I am John Lopez. I am a senior research engineer at the University of Bordeaux. And the topic of my talk today is to introduce the webinar. So the title is Why Beam Shaping for Laser Micromachining. So the first question is, what is micromachining? So it's my definition. It's machining with dimension, tolerances, or affected zone at a micro scale. A good process in micromachining, in general, is a trade-off, is a good trade-off between quality issues, such as technical value, reliability, and cost issues, for instance, buying cost, cost of ownership, or productivity. Laser micromachining has many markets. Some of them are consumer electronic, for instance, for pixel repair or for glass cutting or for glass drilling as well for molding industry, for engraving a pattern of a very clean surface. There are a lot of applications on the medical side for medical device, for instance, for stent cutting, but as well for surgical tool marking or for in-volume anti-counterfeiting marking on syringe or on vials. There are some applications as well on watch industry, on moving parts, but also on some decorative parts on the face, on the front face of the watch. A lot of applications are on for microelectronic and semiconductor industries. For instance, PCB drilling, but also interposer drilling in interposer in silicon or in glass. In photovoltaics industry, the main laser application is P1, P2, and P3 patterning, but there are a lot, many applications in drilling, for instance, in PV industry. There are other markets such as, for instance, automotive industry, for injection nozzle drilling, and so on, and micro machining for mechanics as well. So, what are the numbers? The laser market share in 2019 was about $15 billion. And if we consider the material processing, it's about a third of that. And so we can consider the laser technology, but we can see the share as well according to the process. So marking, macro, and micro. And you will see that micro represents about 31% of material processing. So the volume in terms of laser sales is about $1.5 billion. So on this slide, you can see some example of micromachining part. This is a stent cut in a polymer, in polylactic polymer with ultra-fast laser. This is a demo sample that can show you that we can be very accurate even on very heat-sensitive material. This is a cochlear implant where the ultra-fast laser will engrave this part to do selective ablation. This is an intraocular implant for eye surgery and cut by ultra-fast laser. And these are two moving parts cut by ultra-fast laser for the watch industry, and the fact that have been cut with a processing head in order to avoid the taper angle on the side. So if we consider a laser in a manufacturing process, we have the laser source, the machine tool, and the target. two main questions are the following. First, how to optimize the processing quality. And second question is how to achieve high throughput. There are several options. The first one is to play with the target parameters, such as, for instance, the material itself, but also roughness and impurities that can change the absorption, and also the cover gas, the pressure of the cover gas and the gas itself. But in general, these parameters are fixed by the application. So the other option is to play with a laser parameter that can be tuned to the application. For instance, we can change the wavelengths to adapt, to change the absorption, to the pulse duration, the rep rate, the pulse energy that can act on the fluence, the average power, and so on. But they can be tuned to the application, but there are some limitation. Indeed, as I will show you for engraving application, we already know that the productivity is related to the average power. The higher the average power, the higher the productivity. So if we want to increase the productivity, either we increase the pulse energy, and by then we increase the fluence, but we already know that with low fluence, we get low quality and low removal rates, and on the other hand, with high fluence, we have low quality and high removal rate. We also know that there is an optimum fluence that depends on the pulse duration, and that for high fluences, they are less efficient. Now, if we increase the rep rate, when the pulse-to-pulse delay is shorter than the mean heat reaction time, we will introduce some heat accumulation. So the temperature of the part will increase pulse after pulse, and we can take benefit from that since it will increase ablation efficiency. But in the meantime, you will increase the thermal load and introduce some detrimental effect due to the residual heat. So, for instance, they can change. We can observe some morphology change and melting pools as well. So the surface will be switched from a smooth and reflective surface to a bumpy and black surface, oxidized surface. And in general, it's difficult to control the geometry of the part. We have demonstrated by the past that we can process metallic surface even with a high average power ultrafast laser up to 100 watt 10 MHz, provided that the overlap is maintained below a certain level. If you go above this level, you will introduce some detrimental effects. But these results were obtained with a polygonal scanner. And the polygonal scanner can be used for any application. So for application that where we can't use polygonal scanner, we find another option. Is there another option? Response is yes. We can play with the laser head and introduce the beam shaping. So in beam shaping, I introduce the beam delivery, beam positioning, and beam focusing as well. And we know that it can bring some new opportunities in terms of process optimization. What is beam shaping? There is two kinds of beam shaping. The first one is temporal beam shaping. The second one is spatial beam shaping. First, let's speak about temporal beam shaping. So this is a single pulse. We can change the temporal intensity profile that, for instance, it's used for welding when you want to manage cooling of the sample. You can also divide the incoming pulse into the several pulses to change the absorption with short delay or with longer delay to burst. And there are some new opportunities, for instance, by using gigahertz burst, you will enhance the ablation efficiency. On the other side, we can use, there are spatial beam shaping. With a DOE or SLM, you can change the intensity profile almost as you want. But one of the most common is the top hat profile. So you switch the Gaussian beam into a top hat beam. And by this means, you will get three main advantages. The first one is that you have high contrast, so you can be very accurate. The second one is that the fluence is quite uniform for the top hat, and then you can obtain, it's very good for selective ablation and to be very accurate on the depth that you want to engrave. And the third advantage is that when you do deep processing, you can get very high aspect ratio pattern. I will show you in a few minutes. You can also divide the beam, do a line of beam, as it will be presented later on, or use a matrix 4x4, for instance. If you are processing dielectric materials, you can change the pulse intensity profile and turn it in very dedicated Taylor beam. And for instance, if you use an Axicon or SLM, you can produce a Bessel beam, even change it. And this is, in fact, the Bessel beam is an interference pattern, the zero order of the interference pattern produced by a conical beam. And by this means, you can produce bulk modification, which is very elongated, intense, and highly localized. And this is good for glass coating, for instance. And with a DOE or, for instance, a phase-on plate, you can produce as well multifocus and change and tune the amount of energy for each focus point. And this, you will, by this means, you will deliver the pulse energy at different level into the sample. And you can combine the two techniques, for instance, for spatio-temporal focusing. So in this application, the incoming beam is in gray. Thanks to a grating, you will divide the beam according to the wavelengths and then recombine the wavelengths. And by this means, you will get the shorter pulse duration only at the focus point. And this is good to avoid nonlinear effect before the focus point. And this is good to obtain very tight focusing. I will finish my talk by two examples. The first one is glass coating. The strategy is to produce bulk modification, which is very intense and uniform and elongated along the glass thickness. Pulse after pulse, you will produce some cracks. Thanks to beam shaping, you control the cracks direction. And so the beam is obtained thanks to an Axicon, but it could be a spatial modulator as well. You control the conical angle, and you can see there below the plasma luminescence by such a Bessel beam. The length of the beam is 1 millimeter. This is into a soda lime glass, and this is a kind of modification that can be produced inside the glass. And we did some calculation. So thanks to this spatial beam shaping, we can produce intense. You can see the temperature of the glass. It's intense, but to go even further, we split the incoming beam into a burst with 4 subpulses, and by this means, by using the burst mode and by changing the conical angle, you can increase the intensity at the zero order of the Bessel beam, and by this means obtain the crack that we want. And we can cut the C glass, thin glass, multi-layer glass, tempered glass, or regular glass. The last example, and then I will finish, is high aspect ratio drilling of polymers with excimer laser. So the target is a polycarbonate, sorry, with regular focusing. So with a Gaussian beam, we obtain such pattern. This is a side view, such a hole. Okay, it's black due because it's polycarbonate, and we can't control the geometry. If we use the top hat, we can obtain a top hat at the surface, and by this means produce 2 twin holes. This is side view, this is top view. And you can see that we can be very thin and very regular, and the aspect ratio goes to 200. Okay, so I hope I show you the interest of beam shaping, and now I let the floor to the next speaker.
Hi, thank you very much, John, for the very nice introduction to today's topic. So it's all right, everything is working. So as I was mentioning, we are having a little bit of technical issue on our side, but it sounds that it should be all right for all of you now. So good morning again. And my name is Gwen. I'm product line manager at Cailabs. So I'm in charge of all the material processing applications in the company. And today I will talk about the beam shaping itself. As John was mentioning, this is a key way to improve laser material processing. And we will discuss 2 different examples. one which was tested with LASEA and one which was tested with ALPhANOV. And on my side, I will describe in both cases what were the optical performance of the system. So I will start with a few words about the company. So Cailabs is a French deep tech company. You can't hear me? Can anybody say in the chat if you can hear me or not? Okay, sounds like you can. Okay, all right. Because I'm talking with one computer and I'm changing the slides with another computer so that you know why I'm a bit mixed up and why I don't look at the camera. Okay, let's carry on. So a few words about the company. We are a French deep tech company. So whatever we are doing is based on a quite innovative technology, which is called MPLC for multiplane light conversion. It's a new way to sync light propagation, and it actually enables a lot of new things in a lot of different applications. So this patented technology has proved to work for different different topics. And we were trusted over the year by different people, among which you can see at the bottom of the slide, Amplitude, Cailabs, KDDI, Nokia, or Safran. But what is exactly MPLC and what it enables so many new things? Actually, MPLC is about multiplane phase transformation. So it means that you have a lot of different phase plates. In between them, you have propagation, and it actually enables to do a lot of things with the light. So we can do freeform beam shaping, meaning that any kind of shape is achievable. Actually, because we have so many phase plates, we also manage to handle the phase in addition to the intensity. This is very important for material processing because it means that you have the very nice shape you want in one plane, but we also manage to control how it propagates before and after that plane. Over the years, we realized that a reflective implementation was more convenient. So now it's implemented this way. You have two mirrors and the light going back and forward in between both mirrors. This mirror is actually textured and it's working more or less similarly. So this is a telecom example. All this is passive and reflective, which enables actually to handle high power and high energy. As you can see as well, one interesting thing is that it can also work with multiple beams as an input or as an output. Now, let me just briefly say what are the different applications that we have. Sorry for that. So we have, as I was mentioning, a lot of telecommunication applications, which were described with the picture of the MPLC. This is for local network. This is a network of the future, so mainly with laboratories. And this is laser communication with satellites. We have a lot of different applications with no product line, like defense application or medical application, which are in Cailabs inside. But today we are here to talk about material processing, and that's where I want to go now. It's the Cailabs product line. Basically, whenever you have a laser in a factory or in a workshop which process goods, which enable the processing of different goods, we want to improve the process, either the quality, either the yield of the process. It can be done with a lot of different lasers. Okay, here we are. And if you don't mind, I forgot to just activate the Q&A session. Let me do it now before I forget. It should be all right now. So let me get back to the point. So we have three different product lines in Cailabs. The first one is Cailabs HP. It's for high power multimode laser. It enables complex shapes. The application of, for example, laser beam welding, laser cutting, or additive manufacturing. And actually, in this kind of application, you need very original shapes, sometimes non-symmetric shapes, actually. We have Cailabs. Basically, it's the way to generate very high quality bezel beams with ultra-short lasers, mainly for glass cutting. But today we are here to talk about Cailabs. Cailabs is our product line, which is enabling top-hat generation and beam splitting with ultra-short pulse laser for microprocessing. And I guess that John has given you already many examples of all the applications of microprocessing. Let me just say that all these products are available both in catalog references or as custom developments. Now it's your time to work a little bit. And let me just send you a survey. So you can see actually that you have here a survey. Maybe you have to scroll down. I'm not so sure how it's on everybody's screen, but you may answer all of these questions. And the idea is to let me know, so that it's helping us in the next minutes of the webinar. What have you already done for improving the yield of your laser material microprocessing? Have you already played with your laser, the average power, or maybe the burst mode of the laser? Have you already looked at how to improve the scanning speed? Maybe you have already tried beam shaping, like top-hat beam shaping, or splitting of the output beam. Maybe you have tried all the things as well. So I will leave you some time to answer the question. Take your time. We are not in a rush. And then we will see what you're answering. So I'm not so sure if everybody is saying all the questions. It should be working. I see that already 25% more or less have answered. I'll give you a few more seconds. Thank you very much for answering. It's pretty interesting, actually. Okay, I guess I will close very soon the survey now. Okay, let me close it and share the result. All right, so you have the answer. Half of you have answered already. Sorry for the one who didn't have time. Well, actually, what we can see that most of you have looked at, I would say, more classical solutions to improve the yield. Of course, if you increase the laser average power, you are able to have a faster yield because you have more energy available. Similarly with the scanning speed. Some of you have already tried beam shaping, and I'm happy about that because it will be very relevant for you to compare what you have done already with what we propose in Cailabs. And I just want to conclude that actually, if you want to see the result, you may have to scroll down on your own screen. And what I want to say about that survey is that actually you may use different solutions at the same time, and that's definitely the best way to improve your yield. With some of our shaping capabilities, they are actually compatible with high-power laser, and they are as well compatible with high-speed scanners. And that's what we will see just now. So I get back to my presentation. So what our shaping capabilities are, and I will be more focused on both applications with LASEA and ALPhANOV that we have done already. So in one case, we wanted to improve the yield with top-hat shapes. We have actually tried the line shape with ALPhANOV, and the idea was to work on surface texturing. We have actually tested splitted beams as well, and we have tried a 1x9 splitter with LASEA for engraving, and that all the process results will be given by my colleagues. What were the optical performance? One point I want to talk about is the depth of focus. Actually, it's extremely important to preserve the depth of focus if you want to have a robust process. And in our cases, we have this reference, which is the Rayleigh range of the Gaussian equivalent beam, meaning the Gaussian beam of the same spot size. And what you can see that with this very nice splitted beams, we managed to get the same beam shape over the Rayleigh range, which is actually quite nice. What is actually even nicer is to manage to do that with a top-hat. It's actually pretty challenging, but what you can see here is we were having an equivalent waste over the width of the line of 15 micrometer, which is giving a Rayleigh range of 600 micrometer, and we managed to have a very nice line in the focus, but we have a very nice line at plus or minus the Rayleigh range as well, as you can see here. So that is actually a key point regarding, I would say, the beam quality of the generated beams that will be described afterward. A few words about the setup. This is actually very important too, because this setup are classical, and that's what we want to say. They are standard industrial setups. So this is the setup that we were using with LASEA, and you can see that it was whatever is standard on their industrial machines. We were using an LS shape, which is one of their standard module, and an LS scan, which is actually one of their standard scanner as well. You just have to add these two lenses, and then you have your very nice beam in the processing plane. All that was done with a very nice Tangle laser from Amplitude. The setup we were using at ALPhANOV was somehow quite similar, meaning that it is a standard industrial setup with a Hurry scan as a scanner, and just an injection telescope to get into our module. One more time, we were using a nice laser from Amplitude, a tangerine laser in that cases. So it's pretty important to see that this setup is not so complicated and is actually what most of you are already using in your femtosecond machines. An important point also to discuss is why are we able to get that kind of stable setup, and why are we able to get that kind of performance? We are able to do that because we stabilize the beam. Actually, femtosecond lasers are very complicated lasers, and they are not extremely stable, I would say. And actually managing the instabilities is key if you want to do beam shaping. It's the same for all beam shapers. If your input is not stable, it's difficult to have a stable output. So what we do in Cailabs is that we start by stabilizing the beam, and then we actually shape it. We do that with a unique feature which we developed based on MPLC and based on mode propagation itself. So when I see this shifted beam as an input, what I see as a Cailabs employee is some energy which is in the main mode, the Gaussian mode, and some energy which is in higher modes. And I kind of share the energy of that beam in this difference beam. Split the energy somehow. All the different modes, because it's an MPLC, they have their own paths. We manage them one by one, and we can give them different physical paths inside the MPLC. So in one way, the energy which is in the Gaussian beam will go through the MPLC and do the nice shape in the processing plane. On the other side, the energy which is in the higher modes, they go in another path, and they end up somewhere else, and we just block it. What does it mean? It means that in any case, even if your beam is not stable, you will have a stable output on your material. The drawback somehow is that, of course, if your beam is not stable, you have energy going here, and you lose some energy. An important point to say that this is a simple example with a shift, but it's enabling actually handling very complex instabilities like defocus, ellipticity, or astigmatism. I'm more or less now at the end of my presentation. Just want to see the quality of the intensity profile itself. So I will be pretty quick on that. This is how it looks like just after the module for the splitted beams. It's a very homogeneous splitted beams. You have 9 beams, and they are with very similar energy. And what is good to see is that it's the same in the processing plane. So we have very homogeneous splitted beams. Now, my last slide is about the same topic, but for the line shape. You can see here that you have a very nice top hat over the whole length of the line. It's actually a 1:20 aspect ratio, so that was pretty difficult. It's actually quite homogeneous over the whole length of the beam, plus or minus 10%, as you can see here. And the last point is that, as you can see, the transition length, meaning the distance needed to go from 0% of the energy to the maximum of the energy, is very small, less than 30 micron for a line which is actually in total 600 micrometer length. So that was the beam quality which we managed to have. So this line was used with ALPhANOV, and that will be discussed with Girolamo at the end of the webinar. And the splitted beams were used by LASEA, and this will be discussed by Jerome in a few seconds. So as I was mentioning, we have to activate his mic from this computer because of the technical issue, but no worry, it's going to work. So now Jerome will explain whatever they have done in LASEA with the splitted beams. So Jerome, can you talk? You should have activated your mic actually. So just give us a second, no worry, it's gonna work in a second. So let me at least start and put his slide maybe. Yes. Apparently, no, we cannot hear you, Jerome. Okay, maybe what we can do, Girolamo, could you make your presentation first, and we will get back to LASEA afterward. Yeah. Okay. Carry on. You have the floor. You can go through your slide, which are a little bit further, and we will manage Jerome in parallel.
Okay, Gwen. Thank you very much. So So I'm Girolamo Mincuzzi. I'm a manager of a microsites processing group of ALPhANOV. And I will talk about the study we carried out with the module of, developed by Cailabs about surface texturing. So just to start, you will have some information here about ALPhANOV, which is a technological center for optic and laser. Is based in Bordeaux, southwest of France. It has been created in 2007, and here you can see some number relative to some figures relative to our activity. I will say that we are divided in 4 departments now. So 3 historical departments. So development of laser source and components, development of a photonic system, and department of laser processing, the one to which I belong. And recently we added a department dedicated to training and safety issues, let's say. So what we do in the laser processing department, so we have a large and vast know-how on laser processing of every kind of material. So let's say transparent materials, metal, and also, as you can see on the left side, composite material, or also biological material. And we have know-how on almost all the laser processing, like cutting, drilling, texturing, 3D fabrication, and whatever. In particular, today, I will talk about surface texturing and surface functionalization. So I will go back a little bit to what John said at the beginning. So imagine you want to process a metallic surface and you have a femtosecond high power laser, and you want to avoid any thermal effect due to the high power you are using. So you have basically 2 choices. Let's say the first one, which is referred as a serial processing, is when your high power laser have a high repetition rate, let's say in the megahertz range. So in this case, you need high scan speed. Polygon mirror, polygon scanners could be an option that deliver the beam up to 100 meters per second, let's say. We have shown recently that by using a 10 megahertz, 350 watts, and jointly with a polygon scanner head delivering the beam at 200 meters per second, we have blackened the surface of a metallic surface, and with a throughput that has been reduced from 30 minutes per square centimeter to 35 seconds per square centimeter. Second option is when your high power lasers have high pulse energy. So let's say in the range of millijoule. In this case, the good option could be the beam shaping. So imagine you have a surface S that you want to process with an energy E and a fluence phi. So you have 2 options, let's say. One is to scan a Gaussian beam over the surface. Let's say this is a serial processing option, or another possibility is just to shot one line top-hat profile, and this could be faster, let's say. There are several technologies to make a top-hat line. I will mention diffractive optical elements or SLM, special light modulators, but they have some limitation, like limitation due to the laser bandwidth or some homogeneity of the profile, which is not as good as we want, or the depth of the field is too short, and sometimes they cannot withstand with high, let's say, damage threshold. Here, in our case, we want to see the potential of a multi-plane light conversion technology in generate line the same that Gwen described before, let's say, so 600 microns times 30 microns, and we want to apply this profile for laser texturing. So here you see the result we got. So we fixed the pulse energy to 35 microjoule, the repetition rate to 100 kilohertz, so leading to an average output power of 3.5 watt, and we scan squares of 7 millimeters times 7 millimeters with a notch of 1.5 micron. And during our test, we varied the fluence in between 0.08 joule per square centimeter to 0.2 joule per square centimeters, and the number of successive passes from 10 to 500. So we measured the reflectivity of the surface, because our target is to reach a reflectivity which is less than 5%, meaning a deep black, let's say. And we identified, let's say, two regions. The first region is correspondent to a fluence of 0.13, more or less, joule per square centimeter, in which passing from 10 to 100 scans, we observe a drastic decrease of the reflectivity down to approximately 5–10%, and followed by a plateau. And a second trend, which is relative to fluence of nearly 0.18 joule per square centimeter, in which we observe a decrease of reflectivity when passing from 10 to 500 nano scans, which is monotonical, and approach 5% in correspondence of 500 passes. What is the difference in terms of morphology? So we carried out an SEM analysis, and you can see when you consider the first group, then the surface morphology evolves from these lips to a creation of isolated area, but which are not really the spikes that we are looking for to have a good, so a good black, a deep black. For the second case, we observe that increasing the number of scans, we obtain at 300, 500 scans, huge, let's say, some spikes with the size of nearly some tenths of micron. Here, you can have more details vision, let's say. And in the last case, so 500 passes, the reflectivity is a little bit higher than 5%. So we want to have a value which is lower than 5%. And so we try to further optimize the process by varying the scan speed. And we obtained a value which are starting from 150 millimeter per second, are lower than 5%. And you can see that in this case, you have the typical characteristic hierarchical structuring with the upper position of a kind of a nanoporosity over the spikes, and which is inspired by the moth, the eye of the moth. So once the feasibility has been shown, we want to go more in deep and compare the results that you can obtain when you use a line toupette or, let's say, a standard Gaussian profile. So we have from one side what we have shown, so a top-part line with fluence of 0.18 joule per square centimeter and overall energy over the surface S of 35 microjoule, which correspond to 3.5 watts, and a repetition rate was used of 100 kilohertz. And we want to compare, for instance, with the Gaussian profile having the same fluence and depositing over the same surface the same energy of 35 microjoule. But in this case, we were unable to obtain spikes. It means that we were unable to make a black surface. So we decided to fully exploit the repetition rate of the laser, which goes up to 2 megahertz, and we consider the case of a Gaussian beam with the same fluence, of course, and same power, but with higher overlapping, let's say, so exploiting the repetition rate of 2 megahertz. In this case, we obtained a reflectivity value which are lower than 5 micron. As you can see, the morphology surface is shows some spikes, but of course you have to consider that in this case the repetition rate is 20 times higher than the case of topatine. So this can be seen more precisely when you plot the reflectivity versus both the dose in the upper part and the processing time in the lower part. So in this case, as you can see, for instance, comparing the line with the Gaussian having the same energy, you are able to reach the same reflectivity, but the Gaussian shows a processing time which is nearly 50 times longer. And if you consider the line and you compare it to the Gaussian with the same power, you have the same reflectivity for the same dose and a similar processing time. But of course, for the Gaussian profile, you have a repetition rate which is much higher. So we can make some observations. So the power as the dose both have a bearing on the surface morphology evolution, as we have seen. So when you consider energy constant, the line profile enable a dramatic reduction of the processing time. When you consider power constant, let's say, line and Gaussian profile enable same value of reflectivity and processing time, but the line enable a drastic reduction of the repetition rate, which is something that you are looking for when your laser have high power due to high pulse energy. Then we have shown different surface morphology related to the beam shape, different shape for same dose and power. So we go to my conclusion. So we have shown a novel approach, the multiplane light conversion for generation of laser line. So Cailabs have developed a specific engineered and specific module to join with an industrial laser. And so the line have a aspect ratio of 20, let's say, and the working time, the time required for processing the surface can be comparable, but you need, for Gaussian profile, a much higher repetition rate. So for the next future, we intend to go on and to make tests with power much higher. So consider a laser with more than 50 watts. So for me, it's fine. I can give the floor to Gwen or to Jérôme.
All right, so we just tried it. Okay. You were talking, Jérôme, so we know it should be working. So Jérôme, you have to activate your mic. It's not activated yet. You have to activate it on your side. Now it's activated. Okay, so it's you now.
Okay, now. Yeah, okay. So, hello everyone. I'm Jérôme Platard from LASEA. I'm an R&D engineer, and now I will show you how to improve productivity using a beam splitting technique in laser microprocess. So in the next slide, I will introduce you who we are as a company, LASEA. So in the next slide, you can see that LASEA is specialized in high precision laser micro machining. We build machines that are able to do a wide array of laser microprocessing, like laser drilling and laser cutting, in which we can obtain a 0-degree conicity flanks thanks to our dedicated module, the LS presets, as well as doing thin film removal, as well as laser welding. We can also do laser marking on different materials, such as metals, ceramics, and also glass. In glass, we can even mark the surface of the glass as well as inside of the volume directly. And we can also do laser texturing and laser engraving on different types of parts and different materials to give different property to the surface and the engravings, like increasing the brightness as well as deeply blacken it, or to give an aesthetical aspect as you wish. We are a team of 72 people, a worldwide company. We have subsidiaries in France, USA, and Switzerland. And in the next slide, you can see that we have a wide array of different machines depending on your particular needs, which ranges from the very compact and cost-effective LS2 up to the big LS5-2 that can include pick-and-place devices and robots and automation, as well as vision, and can be fully integrated in your production chain if needed. In the next slide, I will now present you our motivation for this study, because in the scope of a research project, we try to improve our processes and the productivity of our machines overall. And we noticed that over the year, the femtosecond laser power available on the market have a rising power. From the earlier years of the discovery of femtosecond laser process technology, only 1 watt output at maximum was available, but rapidly we saw something which is a standard now, that are the 20 watt output laser sources now as industrial solution on the market for lasers. But recently in the years, we see an increase in power available from this industrial laser with some 100 watt power laser, as well as very recently 300 watt possibility for femtosecond laser output. And we expect in the next few years to have laser sources that can have an output up to 1 kilowatt in femtosecond regime. So, but on the other side, we see that in the laser process, we can increase the energy to increase the ablated volume, and so the productivity of a dedicated machine. But if we see it as an efficiency, which is the ablated volume per energy per second, there is a maximum at a specific energy. And this means that increasing the energy for one single beam is not the best solution to use at its maximum the output of these high power lasers. So in the next slide, the two next slides, thank you. We present you the setup that we use to implement a multi-beam strategy in our standard machine system to increase the productivity by splitting the beam and maintain the energy at the optimum for each of these beams. So we had a partnership with Cailabs, providing us a Canon Pulse module to split the beam into 9 different beams that we used on the target with 2 different strategies that you can see on the next slide, which are a line strategy for testing engravings, as well as a run strategy that you can see at the right to drill holes. So in the next slide, we will show you the results here in the next slide. So on the left, you can see 9 line engravings thanks to the Canada module and the splitting strategy, as well as just below the depth results for these engravings, and you see that the homogeneity of the depth over the 9 beam is excellent. As well as on the right, you can see the result of a drilling of holes that we can achieve with this module, and this the quality of the holes are in line with the performance that we need for most of our processes of drillings. So in the next slide, I will finish with little conclusions, which is that we managed to increase by 9 times the productivity by maintaining the optimal fluence and using it at its optimum the full output of a high power femtosecond laser, while having an excellent homogeneity over the results for the engraving. And as an outlook, we seek to test different beam configuration and continue to test this kind of techniques and to integrate it in our machines, as well as to improve the drilling results and the shape to be even better than what we have now. I thank you for your attention, and I think I will let now Gwen talk for the question and answer. Thank you very much.
All right, thank you. Thank you all for your talk. So now I should be talking again, talking with one computer and still having the control with another one. Thank you, John, for your help. So don't hesitate to ask questions in the chat. Even during the Q&A session, they will be still added to the list of questions, and we will try to answer all of them. So just as a short conclusion on that, we have demonstrated that it's possible with beam shaping to improve the yield with 2 different strategies, one with beam splitting, the other one with top hat shaping, and for 2 different applications, engraving and surface texturing. And whatever we have done in both cases was really high quality free-form beam shapers, preserving the depth of focus, compatible with industrial setups. So I hope that we will have a new result, as Girolamo and Jerome were mentioning, with our partners to keep improving the processes yield and the quality improvement. And now we will start answering questions, and I will try to orientate the question to see who should answer each of them. So you can activate your camera, Girolamo, John, and Jerome, if you wish. So I know that there is one for John first. Okay, so this one was for John.
This is obtained thanks to another beam shaping technique. I don't like to disclose that, but it's patented. But it's common. It's spatial beam shaping as well with a passive element.
All right, so this is another question. I guess this one was for me. Is it possible to change the shape during the process? How long does it take for changing the shape? So what we do in Cailabs, I would say for now, is fixed beam shaping. So when you do the process, you cannot switch from square to round in a few seconds. It's not possible yet. What you can do, and we have done that actually with Girolamo, is changing the shape dimension, and you have to adapt a little bit the optical setup to change the beam dimension, make it smaller, make it bigger. Actually, with Jerome, we plan to do next week or the following week, kind of the same things, but more automatic actually. So again, changing only the shape. We have long-term plan to develop. I would say something which is multi-static shape, meaning that you will have to choose between 5 different shapes. We have done that already, but only from beam splitting. So you could have a module where within a few milliseconds, you can switch from a 1 to 1x9 beam splitter to 1x3 beam splitter this is not available yet for the top chips. I hope this answers the question. So I think actually the next one is for me too. Adalite is reflective and passes through another medium. Is there any HRS to deal with it if needed? Actually, I'm not so sure if there. Girolamo, could that one be for you? I'm not so sure actually to understand it.
Yeah, I think he just want to know if you have losses in terms of reflectivity when the light passes through the module.
Okay. Yeah, but then in that case, actually, the answer also depends on the application. In the case of actually Girolamo case with ALPhANOV, the losses were around the transmission was around 75%. But the thing is that we were having this beam stabilization, so it actually depends a lot on the laser. So with another laser, we could have actually more transmission, and maybe with another laser we could have less as well. In the case of beam splitting, the transmission was much higher, more than 95%, because we don't have beam stabilization. So that's the key point to answer that. The next one is for me too, and I think, of course, that will be my question, and then it should be yours, Geronimo. So what is the minimum distance between spot that we can do in beam splitting? There are two ways to answer that. One thing is that we are very much limited, like everybody, by interferences, and we don't want to generate interferences in between the different spots. So the minimum distance depends on the spot size. We cannot have a pitch which is the same, the pitch in between spots, which is the same dimension as the spot itself. We should have some space in between the spots, where they don't interfere. On the other side, the spot size is actually limited as well by globally the setup and the numerical aperture of the setup, which is fixed by basically the f theta focal length and the scanner aperture. So I would say I cannot answer. It should be possible to do very small pitch, but it depends on the spot diameter that you want to have. How do you handle energy losses? Do you have tested the thermal behavior during the process? So how do we handle energy losses? Actually, we didn't do anything. We lose energy, but once we have our transmission, it's actually quite fixed. It doesn't change much. And do we have we tested the thermal behavior during the process? Maybe Girolamo, you can give an input on that as you were doing the process.
Yes, I confirm that we didn't observe so much changes in terms of transmission, but this is really the question we want to answer with the next step. As I said in conclusion, we are aiming to make tests with more than 50 watts, so maybe we can give you a more precise answer after the test will be carried out. For the moment, it seems to be stable.
All right, thank you, Girolamo. So I guess now we will go to the question about your presentation. So this is for you.
So what is the angle dependence when you measure the reflectivity? Yeah, of course, there is an angle dependence. So we carried out measurement at more or less plus minus 20 degrees respect to the normal. And we did observe variation for the moment. So let's say for according to our experience, if you stay in more or less 20 degrees, the reflectivity is the same. But I will say that in light of the mechanism that is at the base of the blackening, so in light of the light trapping that we can manage to make when using the morphology I show, I think that I don't expect to observe a huge variation when I increase the angle. Yeah, so the measurement of reflectivity is relative to the value I show is relative to green, so 530 nanometers, and we have carried out also a reflectivity measure over a wider spectrum, so up to 2.5 micron at a 90 degree of reflectance, and the reflectivity never exceed 5%.
All right, thank you, Jerome. I guess the next one will be for Jerome.
Yeah, so the answer is simple. Yes, the 9 lines here are realized in a single pass because the Canon Daples module from Cailabs generates 9 different beams at the same time that goes through the scanner at the same time and are marked at the same time.
Okay, I will take that one. I think I somehow answered that in another question as well. The smallest beam size for now we have done is around 30 micron. Actually, it would be possible to do smaller. I guess that we will try to get down to around 10 micron. Then the thing is that if you want to do it even smaller beams, it starts to be complicated due to the numerical aperture of the setup. So somehow, if you are working with standard f-theta and standard scanners, it's not possible. It's not about the technology. It's just about the law of physics. It's not possible to do a top hat of really very, very small dimension, or you need to have a very open optics, which is generally not the case. But still, I would say that the limitation is not on the beam side, but more on the setup. Will we have the webinar recording? I guess it's yes. Okay, so maybe Jerome, you can take that one.
Sounds like a challenge.
Yes, because most of our applications are confidential, but I suppose that probably in most applications where you would like to increase the yield of your process and that you have a sufficient power in your laser to split the beam in the amount of beams you want on your material or on your parts. It's possible in theory, I suppose. Yeah.
John Girolamo, if you want to add also some of your inputs, go ahead.
Yeah, we have shown that it's possible, for instance, to make a cutting of small work pieces for electronics or for mechanical or for watch industry, like gears. We have shown during a conference that you can cut at the same time. So with the parallel processing, we have shown up to 4 gears. I will cite also probably refractive index modification in glass that could be carried out with the parallel processing. So all the process you can make in parallel, then beam splitting can be useful, is required.
Yes, beam splitting is used since I think 30 years now with CO2 laser for cigarette paper drilling or for paper drilling. But it's with a CO2. But the point there is to have a tool, a small tool that can divide the beam and stabilize the beam. And between different beam, the energy is the same, the intensity, shape, profile is the same. And this is a good point. So there is a need for beam splitting, and this is a new tool for beam splitting.
Thank you. That one is for me. So what is the entrance pupil or the aperture dimension of the MPLC module? One of our challenge last year was to develop standard module to have, I would say, catalog references. And for the catalog references, the input waste has to be 500 micrometer. It should be possible. I mean, it is actually possible to have different input beams. It's just that it's custom development, so not everything is possible, but smaller or a little bit smaller or a little bit higher is possible, but 500 micrometer waste is good as an input of our modules. And I see that there is one complicated one after that. Is it possible to make interfere the splitted beams in order to generate Bessel beams, for example? this is not an easy one. I can try to answer, but if you want to add some things afterward, you may add some inputs as well. Well, if you want to generate Bessel beams, basically you have to have interference based from a conical phase beam. So most of the time you generate it with something which is conical, like either a conical axicon in a reflective way. This is the way we do it at Cailabs. Or actually, you can do it also with you can do it with SLMs, and you can also do it with transmissive axicon, which have a conical face. So if you split beams, two Gaussian beams, and you make them interfere, it will not make a Bessel beam. What you could do still is that you could imagine setup where you split beams and you generate two Bessel beams or things like that. But generated the standard Bessel beams, which are rotationally symmetric, with just two splitted beams seems complicated, I guess. And I think that was the last question. So if there are no more questions, I think we will close that webinar. I want to thank you all for participating, and thank you, John, Jerome, and Girolamo for your participation as well. And talk to you later. Thank you very much again, and have a nice day.
Thank you. Bye. Thank you, everyone. Bye.